Aubrey. All right. I can make no guarantee that account is his. Might be mine. I don't This is brilliant.
All right, here we go. Yeah, well, I didn't expect that to come up on the screen, but yeah, I was actually thinking at one point of giving a talk about relationships, because I was so outraged at Chris Peterson's talk at Ephemeral last summer, but I don't think that's what you came for, so I won't give that. Right, here we go. So I'm going to talk about some updates. I know most of you, or many of you anyway, are quite familiar with the work that Sense Research Foundation does, because I've been giving talks like this to this sort of audience for quite a while. But we are moving pretty fast at the moment in terms of the research that's actually happening, both the research that we're doing and work that's being done by other people, but that's relevant to the whole approach that we've been pursuing for the past decade or so. And so I thought I would try and give some updates. I'm going to spend maybe 5 minutes just giving background stuff for those of you who are not familiar with this work. This is the foundation that has been created around my work. It's based in Mountain View, California, and we're a 501c3 public charity, so any billionaires in the audience, please see me later. And we're working on regenerative medicine to defeat aging. This is our spiffing new website that was launched only a week or two ago, and there's a billion times more that you can find there than I'm going to have time to squeeze into the next 15 minutes. But yes, it's really moving quite fast now. Regenerative medicine, of course, you've heard of stem cell therapy, you've heard of tissue engineering. It's all about restoring the function of the body or of some tissue by restoring its structure. And we do regenerative medicine of the classical type, stem cell therapies and so on, but we're also interested in things that are normally outside the conventional definition of regenerative medicine. Things that you might call molecular regenerative medicine, repairing the internal structure of cells, for example. And a lot of that stuff is relevant to the application of regenerative medicine to aging. Aging is essentially a side effect of being alive in the first place. If you look at this definition, this is something that really everybody already knows, but it does bear spelling out, because people can often adopt other definitions of aging that are very confusing and counterproductive for the process of developing interventions. This definition embodies the key things that you really need to understand about aging. First of all, that it's a side effect of the normal operation of the human body. Metabolism is the word that biologists use to denote that. And second of all, that the way that being alive causes the sickness of old age is via the lifelong accumulation of molecular and cellular changes in the body that the body is set up to tolerate a certain amount of, because otherwise we wouldn't get old enough to reproduce and we wouldn't be here. But it's not set up to tolerate an indefinite amount of that stuff, so eventually we have too much, and that's when the diseases and disabilities of old age emerge and progress. So aging is not magic. Aging is not this thing that's separate from the diseases of old age. The diseases of old age are diseases of old age that don't affect young adults precisely because they are aspects of the later stages of something that goes on throughout life. And that's why it makes sense to think of aging as something that is amenable in principle to medical intervention. So essentially, treatment of aging is no more and no less than preventative geriatrics, preventative medicine for the diseases of old age. So I've just mentioned the word geriatrics. If we look at this little diagram, we can see one big reason why this definition of aging that I've depicted again down the bottom is useful. It distinguishes the geriatrics approach to combating aging from what I'm going to call the gerontology approach. So geriatric medicine today essentially means treating the diseases of old age just like any other disease. It means characterizing the symptoms and banging away at them and trying to eliminate the disease from the body. If you think about it, that's obviously completely backwards. It's completely fucked up, because aging is a side effect of being alive. This is going to happen if we carry on being alive, if we do things that are non-negotiable, like breathing, and eating. So it's actually completely hopeless to try to eliminate these diseases from the body. The best that geriatric medicine will ever do is slightly postpone the ill health of old age. And that's just not good enough. So various people have, since a long time before me, have come along and pointed this out, and they've said, well, maybe prevention is better than cure. Maybe we can go in earlier on in the chain of events and somehow slow down the rate at which metabolism, the normal operation of the body, creates these various types of damage in the first place. And that's a nice idea, but unfortunately, metabolism is rather complicated. And it's basically completely impossible to imagine that we could actually tweak this process in some way so as to substantially reduce the rate at which it does something we don't want it to do, namely creation of damage, without at the same time having unintended side effects that do more harm than good. It's completely hopeless. It's not doomed in principle, this approach, but it is an idea whose time has emphatically not come. Absolutely, it's not come. In fact, of course, I'm understating the problem here, because this here is a simplified diagram of a small subset of what we know about how the body really works, and even that is completely dwarfed by the astronomical amount that we don't know about how the body works, even ignoring all the stuff that we don't even know that we don't know. So there's no way this is going to work. But luckily, there's a third approach that we can try. And this is an approach that was pretty much neglected entirely until I started to propound it about 12 years ago. The idea here is that rather than trying to slow down the process where metabolism creates damage, or indeed the process where damage causes these pathologies of old age, instead we separate those two processes from each other by diving in the middle and repairing periodically the damage so that it can carry on being created, but it won't get to the pathogenic level of abundance. And it just so happens that when one comes down to actual practical implementation of this, what it actually means biologically, we can actually answer this question in a very encouraging way. This is what I'm talking about, these various types of damage, these intermediates between metabolism and pathology. Every single one of them, it seems, can be classified into one or another of these 7 categories. And as you can see, these categories are proper, bona fide, down-to-earth biological phenomena. You know, cells dying and not being automatically replaced by the division of other cells. That obviously results in progressive cell loss. And you can go down this list. There are 2 ways in which you can have too many cells. There are various molecular problems, 2 of them inside the cell, 2 of them outside the cell. That seems to be all there is. Now, of course, that's a very controversial statement, but it seems to be true, not only because all 7 of these things have been the topic of extremely diverse and powerful biological investigation for more than 30 years, sometimes a lot longer than that, and that list has not got any longer in that time, but also because I've actually been putting it out in this way, this particular challenge, saying, listen, I believe this is an exhaustive classification. I've been doing that for at least 10 years now, and I seem to be getting away with it. This classification does seem genuinely to be standing the test of time. So that's pretty good news. But here's the really good news, and this is, I think, the last slide that I have that is background that you will have all seen before. I've got the same list on the left-hand side, the subdivision of the problem into these 7 different sub-problems. On the right is the approaches that we think can be used in principle as the maintenance approach, the repair of these various types of damage. Clearly, you all know what stem cell therapy is. If you think about it, stem cell therapy is no more and no less than the replacement of cells that have been lost, the repair of that particular type of damage. We can go down this list and look at other things, ways to remove cells that are dividing when we would rather they didn't, ways to remove cells that are not dying when we'd rather they would, ways to make mitochondrial mutations harmless. I'm going to talk about a couple of these things in more detail because I think it's going to be interesting for many of you to get some more recent information about how all of this is going. And the first one I'm going to talk about is these cells, death-resistant cells. Lots of people ignore these. They don't realize that actually there are times in the body when cells need to die, and when they don't die, there are problems. One great example in human aging is the immune system, where cells can often get into a state where they no longer respond appropriately when an infection happens, but also they just fill up space and they inhibit the proliferation of other cells. This is a paper that came out just 2 years ago now, and it's being followed up very aggressively. Essentially what these researchers did, this is not work done by us, but it's very related. They created a genetically modified mouse that accumulated death-resistant cells at an accelerated rate, and sure enough, the mouse wasn't terribly happy, died at less than half the typical age of a mouse. This mouse was less than 1 year old, and as you can see, it's pretty miserable. They also genetically modified these mice so that they could artificially kill off all of those death-resistant cells just by giving a drug, just by giving a simple drug. You can't the simple drug would have no effect on unmodified organisms, but it worked fine for these ones. And therefore, they were able to demonstrate by proof of concept that if you did this, even relatively late in the lifespan of these organisms, that they could be protected from the accumulation of these cells, and sure enough, that protection was at the functional level. They measured dozens of different things in these mice in terms of biological age, and the results were completely unequivocal and very dramatic. So that's really pretty good news. Now, the next thing I want to talk about is work that Sense Research Foundation has done, and this is sort of a flagship project of ours. It's something that we've been pursuing for several years now, because it is really very hard, very ambitious, too ambitious for most cowardly people to actually try it. But this is why Sense Foundation exists, to do the really hard parts of the defeat of aging. Cardiovascular disease is the #1 killer in the Western world, as I'm sure you all know. And this is the beginning of cardiovascular disease. White blood cells go into the artery walls, the walls of our major arteries, for the purpose of cleaning up detritus, garbage that has got stuck there. A lot of that garbage is made of cholesterol. Now, cholesterol itself is not a harmful molecule, in case any of you are doubting that. Cholesterol is a molecule that we need. The problem is that occasionally it gets chemically modified, it becomes oxidized cholesterol, and oxidized cholesterol is toxic. These white blood cells that go into the artery wall are very good at processing and recycling normal cholesterol, but they get poisoned by this oxidized cholesterol, and this is what they become, something called a foam cell, and this part of the cell, the lysosome, is the part that gets poisoned. We are working at Rice University in Houston on a way of fixing this, and we're actually working on a very similar project to address macular degeneration, the #1 cause of blindness in the elderly, in the same sort of way that I'm going to be describing for cardiovascular disease. That macular degeneration project is one of the ones that's happening at our research center in Mountain View. So this is what we want to do. What we want to do is exploit the ingenuity of microbes, of bacteria. It turns out that in the environment, there's a massive diversity of bacteria that have evolved to be able to metabolize and live off very unusual substances. And we reasoned some years ago that it might be possible to identify bacteria which could eat oxidized cholesterol. Now, the idea was not to inject such bacteria into the body, because bacteria like that can probably eat plenty of other things as well that we'd rather they didn't, and so there might be side effects that we wouldn't like. But what we might be able to do is to identify the genetic basis of how they do it, the genes and enzymes that they use to break down oxidized cholesterol, and then augment the degradation capacity of our own cells so as to fix that problem. This is basically what I'm saying. There's a process in the body that turns young people into old people, and eventually into dead people. And then there's another process that turns dead people into decomposed people, and that's encoded in the microbes of the environment. We do standard biology on that, molecular cell biology, and we modify our own cells as a result so as to counteract the process that turned young people into old people in the first place. So step 1 in all of that is to find bacteria that do what we want. And way back 5 years ago, this is the first paper that was published from work funded by Sense Research Foundation, actually. We were able to show that we could find such bacteria to break down this one particular type of oxidized cholesterol. It seems to be public enemy #1, the most toxic, the most abundant. What we're doing here is what's called an enrichment culture, in which most of the bacteria that we are trying out this stuff on can't do anything with it. We just give them 7-ketocholesterol to eat, we don't give them anything else, and they just sit there like lemons and nothing happens. The other two, however, these two strains have a whale of a time, and after only 10 days the material is completely gone. So that's great, and we were able to show that 5 years ago. We were also able to show, pretty soon after that, how they were doing it. We were able to identify genes and enzymes that were involved in the degradation of 7-ketocholesterol. What's taken a good deal longer is to adapt those enzymes, to modify them so that we can put them into mammalian cells in cell culture and make them work. But now we've done that too. On this graph, which is published from a paper that came out less than a year ago, and which we are very proud of indeed, we're showing essentially that if you have a completely insupportable amount of this 7-ketocholesterol, then the cells are history, whatever happens. But if you've got more modest concentrations of this stuff, then cells that have this particular enzyme directed to the lysosome, which is where it's needed, do a lot better in terms of survival than various negative controls, like ones that don't have any enzyme, or ones that have the wrong enzyme, or ones that have the enzyme directed to the wrong part of the cell. So we're very proud of that, and we expect that within a year we will be developing this in mouse models of cardiovascular disease, and maybe also in the parallel project for mouse models of macular degeneration. Now, of course, we still have a long way to go, that's for sure. I've told you about steps 1 through 4 here. As I say, we may be able to get onto mice fairly soon, and then only after that works will we be able to talk about clinical trials. So this is a very long-term, ambitious, high-risk project. But if nobody were doing those high-risk projects in any technological field, whether medical or otherwise, then technology would move a great deal more slowly than it actually does. So I'm very proud to be spearheading this organization. I'm going to stop there and just remind you why this is rather important. The fact that most people would prefer to be like this guy on the left, even if he is about to have his head bitten off by a shark. And that it's not just me that this relies upon. Every single person in this room can contribute to hastening the development of technology that stops this from happening. Everybody. Maybe you're a biologist, maybe you're a billionaire, maybe you're just able to engage in advocacy, you know, to interview me or my colleagues at Sense Research Foundation, to have us give talks at conferences, anything like that. Talk to your friends, talk to your colleagues, talk to anyone. Just make sure that we educate people to understand that aging is a legitimate target for medical control, medical intervention, and that it actually will give far the best bang for the buck of any type of medical research. Thank you.
Thank you so much, Aubrey.